The night sky looks calm, almost static. Stars appear fixed, and the darkness between them seems empty. That picture is comforting, but it is not accurate. Across the universe, large-scale events are unfolding quietly, without visible warnings, and some of them carry consequences that are hard to overstate. For a long time we treated interstellar space as mostly empty and mostly safe. We assumed that truly dangerous objects were rare and that the ones that existed would announce themselves through light or other radiation. In 2025, those assumptions took a serious hit. Astronomers at UC Berkeley reported a detection that should have reshaped how we imagine our galaxy. They found a black hole that is not orbiting a star and not embedded in any recognizable system. It is moving through the Milky Way alone. The object is catalogued as MOA 2011 BLG 1491. Its mass is estimated to be between 1.6 and 4.4 times the mass of the Sun. What makes this discovery striking is not only the black hole itself, but the way it had to be found. The team used gravitational microlensing, a method that lets you detect a massive, invisible body by watching how it bends the light of a more distant star. In this case, the black hole passed almost exactly between Earth and a background star. The gravity of the black hole curved space-time enough to focus the star's light toward us, making the star appear brighter for a short period. Then the alignment ended. The star returned to normal, and the black hole continued on its path. The black hole did not emit light, radio waves, or X-rays that we could pick up. It revealed itself only through gravity. That matters because microlensing detections require extraordinary geometry. A lensing object must cross the narrow line of sight between a telescope and a suitable background star. The odds of catching such an event are extremely low, so the fact that we have observed one wandering black hole like this implies a larger hidden population. If one was spotted in a tiny observational window, many more must exist outside that window. Current theoretical work allows for millions and possibly billions of free-floating black holes in the Milky Way. These objects are effectively invisible under normal circumstances. They do not shine, and unless they interact violently with gas or stars, they produce no obvious signature. We should think of them as massive bodies moving through the galaxy without warning signs that conventional astronomy can easily track. The Gaia space mission is expected to push this picture further. Gaia is mapping the positions and motions of more than 1 billion stars with precision that has no historical parallel. As its dataset grows, astronomers expect to register hundreds or even thousands of new microlensing events. Each event would point to another unseen compact object, potentially another black hole, that we had not known was there. The Milky Way may be filled with drifting, dark masses that only occasionally reveal themselves by distorting the light of distant stars. So the empty space between stars is not empty at all. It is a dynamic environment where invisible compact objects can move across stellar neighborhoods. Even if most of them pass harmlessly far from any planetary system, the scale of the population changes the statistical reality of what can happen over cosmic time. But wandering black holes were not the only surprise of 2025. Another one cuts even deeper because it touches the basic direction of the universe itself. The Dark Energy Spectroscopic Instrument, or DESI, released results from its first year of observations. For decades, cosmology has been built around a standard model known as LCDM. In that framework, dark energy, the component driving the accelerating expansion of the universe, is treated as a cosmological constant. In simple terms, it is assumed to be unchanging in time and uniform in space. DESI's early data challenges that assumption. The analysis suggests that dark energy may evolve over cosmic history, meaning its strength or behavior could vary as the universe expands. Researchers describe dark energy using an equation of state parameter, usually written as W. If dark energy is truly constant, W should be exactly 1. DESI's results hint that W might not stay fixed and may instead change slowly with time. This is not yet a final verdict. The statistical significance of the deviation is reported in the range of about 2.6 to 3.9 sigma. In physics, that level is a strong reason to pay attention, but not strong enough to declare a discovery. Scientists are careful here, but they are not dismissing the signal, because if it holds up, it alters the most basic predictions we make about the future of the cosmos. Why does an evolving dark energy matter so much? Because the fate of the universe depends on what dark energy does next. If it is constant, then expansion continues forever in a way we can model. If it evolves, several radically different outcomes become possible. One option is that acceleration slows, changing the long-term thermal and structural future of galaxies. Another possibility is that dark energy grows stronger with time. In some models, that behavior corresponds to phantom energy, where W drops below 1. If dark energy behaves that way, the universe might not just expand indefinitely. Expansion could accelerate to the point where gravitationally bound structures cannot hold together. In the scenario known as the Big Rip, the increasing acceleration first pulls galaxies apart, then star systems, then planets, and eventually overcomes forces holding matter together at the atomic level. The key point is not the label, but the implication. A changing dark energy makes the end point of the universe uncertain in a way that LCDM does not allow. DESI's findings therefore do more than tweak a parameter. They question the stability of the model that has guided modern cosmology for decades. When the foundational assumption shifts, every conclusion built on top of it becomes provisional. The universe may be filled with hidden massive objects we cannot see, while being driven by a background force we do not fully understand. The calm surface we observe from Earth can hide processes that operate on scales and with effects far beyond our everyday intuition. With that in mind, the next question becomes unavoidable. If rogue black holes are common, how do they form, and what happens when one passes through a region like ours? To understand why a black hole can end up drifting alone, you have to look at how violent its birth environment can be. When two black holes merge, they release gravitational waves in an asymmetric pattern. That imbalance can kick the newly formed remnant away at high speed. In some cases, the recoil is strong enough to eject it from its original system entirely, leaving it to travel through the galaxy on its own. A similar outcome can happen at the moment a black hole forms from a massive star. If the collapse and the supernova are not perfectly symmetric, the newborn black hole receives a gravitational kick. The star that used to anchor it is gone, and the black hole can be launched into interstellar space. Dense stellar regions add another route. In globular clusters and other packed environments, close gravitational encounters between massive objects are common. Over time, those interactions can sling compact remnants outward, sometimes expelling them from the cluster altogether. So there are multiple, well-understood mechanisms that can populate a galaxy with free-floating black holes. The object MOA 2011, BLG 191, fits that picture. It was detected through a microlensing event that lasted long enough for astronomers to estimate its mass reliably. The duration of a microlensing signal is not just a curiosity. Short events usually indicate lower mass lenses like planets. Longer events often point to heavier bodies, and compact objects can stretch the signal to weeks or months. In this case, the timescale matched an object in the black hole mass range, and the team found no evidence of a companion star. The simplest reading is that it is a black hole formed in a stellar death event, now moving through the Milky Way alone. If one such object was caught by chance, the underlying population must be much larger. Models that track the full history of stellar evolution in the Milky Way allow for millions of rogue black holes. Some projections push the number higher into the billions, depending on how efficiently massive stars form and how often remnants are expelled over the galaxy's roughly 13 billion year lifetime. These numbers matter because they turn an isolated detection into a statistical problem. We are not talking about a single odd case. We are talking about a hidden component of the galaxy. Most of these black holes are moving quietly through regions we do not routinely monitor. The reason we miss them is simple. Microlensing searches depend on dense fields of background stars and long continuous monitoring. Even then, we only detect objects that cross an exact line of sight to a bright enough source. That geometry is rare, so even with modern surveys, we are probably seeing only a small fraction of the real rogue black hole population. The rest remain undetected because they do not emit light and they do not advertise their presence until a chance alignment exposes them. That leads to the question that follows naturally from the numbers. What happens if one of these objects passes through a planetary system? It does not need to collide with anything. At distances far larger than a planet's orbital radius, a black hole's gravity can still perturb the paths of planets, asteroids, and comets. The first effects might be subtle, a slight change in eccentricity here, or a small shift in inclination there. But gravity acts continuously, and small changes do not stay small when they accumulate. Over long periods, those perturbations can push a stable system into chaos. Outer planets can drift into new resonances that destabilize inner orbits. Dwarf planets and asteroid belts can be scattered. Comets can be driven inward in large numbers, creating a sustained bombardment phase. And in the most extreme case, a close passage can eject planets entirely, turning them into unbound worlds that wander interstellar space forever. The black hole itself continues on its trajectory almost unaffected. It leaves behind a system that may look normal from a distance, but has been fundamentally altered. The disturbing part is how little warning such a passage would give us. A rogue black hole does not brighten as it approaches. It does not leave a trail. We would not see it coming in any straightforward way. The first sign could be a growing instability in orbital data that seems to have no external cause, and by then there is no corrective action we could take. This is not like an asteroid you can, in principle, deflect with enough preparation. A compact object several solar masses in size is not something you can push away. If it crosses your neighborhood, you can only measure the consequences. Now, even if the galaxy holds millions of rogue black holes, space is still vast. The average distance between such objects is huge, and most of them will never come near any particular system. But never changes meaning when you consider billions of years. Over cosmic time, low probability events become inevitable somewhere. The risk is not that a black hole will pass close to Earth next year. The risk is that the Milky Way is not a quiet backdrop. It is a place where rare, invisible encounters can reshape systems without leaving any obvious trace of the intruder. And it is not only mature planetary systems that are vulnerable. The earlier stages of star and planet formation are even more sensitive. A protostellar nursery relies on a delicate balance between gravitational infall and thermal pressure. A passing compact object distorts that balance. If a rogue black hole passes through a protostellar cloud or a protoplanetary disk, its gravity can trigger rapid collapse in some regions while tearing others apart. That can lead to abnormal star formation rates, premature fragmentation, or large-scale instabilities that destroy the disk structure altogether. Any planets trying to assemble in that environment may never form, or they may form on unstable paths from the start. So the discovery of wandering black holes is not only about counting hidden objects, it forces us to think differently about how stable a galaxy really is, and about the unseen influences that can operate in the background. We are beginning to map these bodies, but the map is still crude. Right now, we do not know how many are in our vicinity, how their orbits distribute through the disk and halo, or how often they pass through star-forming regions. What we do know is that they exist, that the detection methods are finally catching up to them, and that their effects are real even when we cannot see the cause directly. Once you accept that, a broader pattern becomes visible. The universe is full of processes that move slowly, silently, and out of sight until their consequences break into view. Rogue black holes are one example, but they are not the only one. And the next phenomenon is even stranger, because it involves stars that simply fade away without a clear physical explanation. A black hole doesn't have to collide with a star to ruin it. If one passes close enough, its gravity produces tidal forces that stretch the star unevenly. The outer layers respond first, but the distortion propagates inward, upsetting pressure and temperature balance in the core. In extreme flybys, this stress can trigger runaway reactions or structural failure that ends in a supernova. The star effectively dies because something massive moved past it. If no one is watching that region at that moment, the event looks like an ordinary supernova with no clear cause. Planets are even more vulnerable to a close passage. Simulations show that a rogue black hole can destabilize a planetary system almost immediately. Some planets are pulled inward and their orbits shrink abruptly, pushing them into hotter, tighter tracks. Others are thrown outward. Their orbits become elongated, and many are eventually ejected completely. Those expelled worlds become rogue or orphan planets objects that used to orbit a star but now drift through interstellar space. They are quiet evidence of catastrophes that may leave no other visible signature. This kind of damage is disturbing partly because it comes without a warning signal. A supernova or a gamma ray burst announces itself with light across the spectrum. A black hole flyby does not. The black hole stays dark and its influence is gravitational. Orbital chaos and stellar instability can unfold over centuries or millennia. By the time an observer realizes a system has been perturbed, the black hole is long gone, leaving only the aftermath. If an advanced civilization were living in such a system, they might detect the disturbance too late to act. The source of the threat would already be light years away, invisible and unreachable. Could something like this happen here? On human timescales, the odds are very low, but over billions of years they are not negligible. The Sun has several billion years left. Across that span, the chance of a close encounter with a rogue black hole becomes a real, if still small, possibility. The uncomfortable truth is that we do not have a catalogue of nearby wandering black holes, and we cannot track what we do not see. A massive object could be moving through the galaxy in our general direction, and we would not know until its effects began to show up in orbital data, at which point nothing could stop it. If unseen predators drifting through space are not enough, there is another danger that comes from the fabric of physics itself. Quantum field theory allows for a scenario called vacuum decay. It is the possibility that what we call empty space is not in the lowest possible energy state. In that case, the universe is only metastable. It can persist for an extremely long time, but a transition to a lower energy vacuum remains possible in principle. Fields fill the universe. The electromagnetic field, quark and lepton fields, and the Higgs field are all examples. Each field has an energy configuration that defines the state of space. The concern is that the current configuration might be a false vacuum, stable for now but not truly minimal. If a lower energy configuration exists, quantum fluctuations could, in theory, nucleate a tiny region of that lower energy state. The Higgs field is the most important candidate in this discussion because it sets particle masses and helps determine the structure of matter. If the Higgs vacuum is metastable, then a small bubble of true vacuum could form. Once formed, it would expand at essentially the speed of light. As it grows, the values of fundamental constants and the behavior of all particles inside it would change. Chemistry, nuclear structure, and the forces that hold matter together would not survive that transition. From the perspective of anything in its path, it would be instantaneous and final. For years, this idea was treated as a remote theoretical curiosity, but recent work has kept it on the table. In 2024, a paper by Lava and Rubio examined vacuum stability in the early universe and argued that conditions soon after the Big Bang could have made metastability more relevant than previously assumed, especially if the early universe went through a phase dominated by kinetic energy rather than radiation. That does not prove vacuum decay is imminent. It strengthens the case that the question is physically meaningful and worth taking seriously. So the universe contains dangers that range from invisible compact objects crossing through star systems to the possibility, however small, that space-time itself could shift into a different state. Both share the same feature. They offer no warning and no defense. The next step is to look at what could trigger vacuum decay and what modern observations tell us about whether our vacuum is truly stable. Could the vacuum we live in be only temporarily stable, with a lower energy state waiting underneath? In modern physics, that possibility is taken seriously enough to study in detail. The main reason is the Higgs field. This field gives elementary particles their masses, and its vacuum state influences the basic structure of matter. If the Higgs field is not in the true lowest energy configuration, then our current vacuum would be a false vacuum. It could persist for an extremely long time and still be unstable in principle. In that picture, the danger is not an ordinary explosion or collapse. The concern is a phase transition. Quantum field theory allows that a tiny region of space could, due to a rare quantum fluctuation or an extreme high-energy event, drop into a lower energy vacuum state. If that happened, a bubble of true vacuum would form. The crucial point is what follows. Calculations show that such a bubble would not remain small. It would expand outward, and the boundary of the expanding region would move at essentially the speed of light. Everything inside the bubble would be governed by different physical parameters. The Higgs field would take a new value, and particle masses would shift with it. That would ripple through the rest of physics. Atomic structure depends on mass ratios and force strengths. Chemistry depends on stable atoms and predictable electron behavior. If those inputs change, the familiar organization of matter fails. The transition would not look like fire or shock waves. It would be more fundamental, the replacement of one consistent set of laws with another. Any complex structures that rely on our present constants, including planets, stars, and life, would simply not be supported in the new regime. What makes this scenario uniquely unsettling is that it offers no warning. An expanding true vacuum bubble cannot be detected in advance by any signal traveling slower than light, because the wall itself moves at light speed. If a bubble formed far away, you would not see it coming. There would be no visible precursor, no energy flash that arrives first, no disturbance that gives time to react. From the point of view of anything in its path, the change is instantaneous. One moment physics is normal. The next moment the bubble wall reaches you, and the conditions that allow matter to exist in its current form are gone. For much of the late 20th century, vacuum decay was treated as a remote theoretical edge case. The reason it returned to the center of discussion is that the stability of the Higgs vacuum is not arbitrary. It depends on measured parameters, especially the mass of the Higgs boson and the mass of the top quark. Those values determine the shape of the Higgs potential, and therefore whether our vacuum is firmly stable or only metastable. The Large Hadron Collider has pushed these measurements to high precision. Data from ATLAS and related analyses have narrowed the allowed ranges. When those numbers are placed into standard calculations, the Higgs vacuum appears to sit close to the boundary between stability and metastability. That does not mean decay is likely. It means the question is not purely philosophical. Our best current inputs do not put the vacuum safely deep inside the stable region. They place it near the edge, where theoretical uncertainties and higher order effects matter. Recent theoretical work has added another layer. In 2024, Lava and Rubio studied vacuum stability during an early universe phase known as kination, a period in which the universe's energy density would have been dominated by kinetic energy rather than radiation. Their analysis showed that under certain conditions in that regime, the Higgs vacuum could have been more unstable than earlier estimates suggested. This result does not say collapse is inevitable or even likely today. What it does say is that the stability history of the vacuum may be more sensitive to cosmological conditions than we assumed. If the vacuum was closer to instability in the past, then the fact that the universe survived to the present could partly be a statistical outcome rather than a guarantee of absolute safety. There is an obvious counterpoint. If metastability were a serious practical threat, why are we still here after 13.8 billion years of cosmic history? Many physicists argue exactly that. Even in metastable models, the predicted lifetime of our vacuum is usually far longer than the current age of the universe. On those timescales, decay would be so rare that treating the vacuum as effectively stable is justified for any human or even stellar timeframe. In addition, the calculations involve assumptions about physics at energies we cannot yet test directly. Small changes in input parameters or unknown high-energy effects could strengthen stability significantly. So the mainstream view remains cautious. Vacuum decay is not considered an imminent disaster. The probabilities inferred from current models are extremely low, and there is no observational sign that a transition is underway anywhere we can see. But the honest position is that the question is not closed. We do not yet have a complete theory that unifies quantum fields and gravity, and we have not mapped the Higgs potential with absolute certainty. The stability boundary could shift as measurements improve. It could also shift if new particles or interactions are discovered, because those would modify the behavior of the Higgs field at high energies. This is why the LHC and future accelerators still matter to cosmology. Every refinement of the Higgs boson mass and the top quark mass slightly adjusts the inferred stability of the vacuum. Each new dataset narrows the uncertainty. Over time, the picture could move deeper into stability or further into metastability. Either way, the outcome would reshape how we think about the long-term future of the universe. The vacuum state is not a background detail. It is the platform on which all structure and all life rests. Taken together with the discovery of free-floating black holes, the message is consistent. Some of the most consequential processes in the universe are silent and hard to predict. They are not loud cataclysms that broadcast themselves across the sky. They are conditions and objects that can exist unnoticed until the moment their effects become unavoidable. With vacuum decay, the effect will be final and universal. With rogue black holes, the effect is local but still capable of erasing the stability of entire systems. The next step is to look at other quiet cosmic threats that operate on different scales. Not all of them involve exotic quantum transitions. Some come from ordinary astrophysics taken to extremes, including stars that vanish in ways we still cannot fully explain. The Big Rip is not a slow fading of the universe. It is a violent ending where nothing survives, not even the geometry of space itself. If dark energy grows stronger over time and the expansion accelerates without limit, then the fabric of the cosmos is pulled apart layer by layer. First, it overwhelms the gravity that holds galaxy clusters together. Then it tears galaxies into isolated star systems. Later, it breaks those systems apart as well, leaving planets and stars unbound. In the final stages, the expansion becomes so extreme that even the forces inside matter cannot resist it. The scenario may be billions of years away if it is real, but the possibility changes how we think about the universe right now. We are not just living in a cosmos that will cool and thin out. We may be living in one that could eventually dismantle itself. Whether Desi's early hints point to that future is still unclear. The data are not decisive. But the fact that the question is even on the table shows how fragile some of our settled cosmological assumptions were. It also sets the tone for what comes next. Some of the most unsettling phenomena in space are not loud explosions. They are quiet processes that unfold in the background and only reveal themselves by what is missing. One example is happening at the scale of galaxies. A galaxy is supposed to be one of the most durable structures in the universe. It forms from gas, stars, and dark matter collapsing together under gravity, and once it exists, it should persist for billions of years. Galaxies collide, merge, and evolve, but they remain visible systems of stars bound to a dark matter halo. In a universe governed by gravity and long-term stability, whole galaxies are not expected to simply fade away. Yet observations are forcing astronomers to reconsider that expectation. In deep surveys, researchers have found a class of objects called ultra-diffuse galaxies. These galaxies are physically large. Some are comparable in diameter to the Milky Way, but they contain far fewer stars. Their surface brightness is so low that they look like almost transparent smudges, even in sensitive instruments. If you are not explicitly searching for them, you can miss them entirely. They are not small dwarf galaxies. They are big systems that appear star-poor, stretched thin, and on the edge of detectability. Some ultra-diffuse galaxies seem to be in the middle of disappearing. Their stars are so spread out and so weakly bound that even moderate tidal forces from nearby massive galaxies or clusters can strip them away. In some cases, we see long, faint streams of stars trailing behind them, evidence that the system is being dismantled. In other cases, the mechanism is not so obvious. The galaxy looks underluminous for its size, as if much of its stellar content is already gone. This is not what standard formation models predicted. It suggests that in some environments, galaxies can be eroded to the point where they effectively cease to exist as coherent, visible structures. The puzzle is not only that these galaxies are fragile, it is that we still do not fully understand why some of them survive while others collapse into nothing. Their internal dynamics are difficult to measure because there are so few stars to track. Their dark matter content is uncertain. Some appear to be unusually rich in dark matter, which should protect them. Others appear to have surprisingly little, which would make them easy to shred. A few ultra-diffuse galaxies even show properties that are hard to reconcile with any neat category. They look too large for their stellar mass, too faint for their supposed halo, or too isolated to have been stripped so strongly. Each new case expands the gap between prediction and observation. That gap matters because it forces a more general question. If there are galaxies that can become nearly invisible or vanish under processes we do not yet quantify well, then there may be a broader population of structures we are failing to detect. In astrophysics, the line between speculation and discovery is often drawn by new instruments. We only find what our surveys are designed to see. Once you accept that, you have to consider possibilities that sound exotic but are built out of known ingredients. This brings us to the darkest ingredient in the universe. Roughly 85% of all matter is dark matter. It does not emit light, it does not absorb light, it interacts with ordinary matter almost entirely through gravity. We infer its existence because galaxies rotate faster than visible mass alone can sustain. We see it in gravitational lensing, where light from distant objects bends around massive structures that contain little or no luminous material. We see it in the large-scale pattern of cosmic structure, which cannot be produced by normal matter alone. Dark matter is not a minor correction. It is the backbone of galaxies and clusters. But if dark matter is so abundant, another question becomes unavoidable. Can it form structures in the same way ordinary matter does? Ordinary matter cools by radiating energy, clumps together, and builds stars, planets, and galaxies. Dark matter does not radiate in any way we can measure. So for a long time it was assumed to remain a diffuse halo, shaping visible systems but never forming compact objects of its own. Some theoretical models challenge that assumption. If dark matter particles have even a weak self-interaction, or if there are multiple dark matter components with different interaction strengths, then they could lose energy through channels we do not detect. Over very long timescales, that would allow dark matter to cool and collapse under its own gravity. In that case, dark matter would not only surround galaxies. It could build its own architecture, dark stars, dark planets, and even dark galaxies that contain little or no ordinary matter. These objects would not look like stars in the usual sense. They would not burn hydrogen. They would not shine. They would be entirely invisible to electromagnetic telescopes. The only way to infer them would be through their gravitational influence, by how they distort light, perturb visible orbits, or change the dynamics of the systems around them. If such structures exist, they would represent a parallel cosmic ecosystem that we are nearly blind to, sharing the same space as the visible universe while leaving almost no direct trace. This idea is still speculative. It depends on properties of dark matter we have not measured, but it is not pure fantasy. It is a logical extension of the fact that dark matter dominates the mass budget of the cosmos, and that gravity does not care whether matter is luminous. If dark matter can clump, then the universe may contain massive compact bodies that are completely dark, just as rogue black holes are completely dark. And that would mean there are more kinds of gravitational actors moving through space than we currently account for. So the pattern deepens. At every scale, from wandering black holes to fading galaxies to hypothetical dark stars, we keep running into the same blind spot. The universe may contain large populations of objects that do not announce themselves with light. They exist, interact, and sometimes destroy while remaining almost invisible to the tools we rely on. The next step is to look at what these dark structures would be made of, how they might form, and what signatures they could leave behind if they inhabit our galaxy. If dark matter can build its own structures, the most extreme outcome would be compact objects rather than smooth, featureless halos. The logic is direct. Gravity acts on mass no matter what it is made of. If dark matter particles are able to shed kinetic energy, even very inefficiently, then over cosmic time they can sink inward and form bound bodies, just as ordinary gas forms stars. The open question is not gravity. The open question is whether dark matter has any mechanism for dissipating energy. In the standard cold dark matter picture, the answer is no. Dark matter is assumed to be cold, meaning its particles move slowly compared with light, and collisionless, meaning they pass through each other without exchanging energy. With no way to radiate or cool, dark matter stays spread out in roughly spherical halos around galaxies. This framework matches a long list of observations. Galaxy rotation curves show that visible matter is not enough to explain how fast stars orbit. Gravitational lensing maps reveal more mass than telescopes can see. Large-scale simulations reproduce the cosmic web only when dark matter is included. So the baseline model works well. But it is still a model built on assumptions we have not yet tested at the particle level. A major alternative gives dark matter a weak self-interaction. If dark matter particles can scatter off each other, or if the dark sector includes more than one component with different interaction strengths, then the halo gains an internal way to redistribute energy. Over very long times, that redistribution can let part of the dark matter cool and contract. The contraction may be slow compared with the lifetime of individual stars, but the universe has had almost 14 billion years to work with. In these models, compact dark objects are a natural endpoint, not because they are demanded by any one observation, but because they follow from gravity plus time once cooling is allowed. Such objects would not radiate like normal stars. Without electromagnetic interactions, dark matter cannot form atoms, cannot ignite nuclear fusion in the usual sense, and cannot shed heat as light. A dark star in this context means a gravitationally bound body made mostly of dark matter, supported by whatever internal pressure or dark sector forces are available. Depending on particle properties, it might be diffuse and large, or dense and compact. Either way, it would be invisible to optical, infrared, radio, or X-ray telescopes. The same reasoning extends to smaller bodies. If dark matter can clump, it could also make dark planets or dark substellar objects, again with no light signature. The idea can be pushed to even higher densities. Ordinary matter ends up as white dwarfs, neutron stars, and black holes. A dark sector with its own interactions might produce something analogous to a neutron star or another stable compact remnant. A dark neutron star would not emit radio pulses, X-rays, or gamma rays. It would not carry an observable magnetosphere. It would simply be a silent gravitational mass. If one moved through a stellar neighborhood, the only evidence would be its gravitational pull on nearby stars or planets. How could we detect bodies like this? Only by gravity. Any massive compact object can act as a lens, bending and magnifying light from a background star. Microlensing surveys already use this effect to find rogue planets and isolated black holes. A dark star would produce a microlensing event with a duration set by its mass and velocity, just like any other compact lens. But lensing reveals mass, not composition. A stellar mass lens with no luminous counterpart is usually labelled a black hole. Yet a purely dark star would look identical in microlensing data. Even with perfect light curves, separating these possibilities is nearly impossible unless there is extra context, such as a population signature or a merger event. Gravitational waves provide a second route. Since the first LIGO detection in 2015, LIGO and Virgo have recorded many mergers of compact objects. Most fit standard templates for black hole or neutron star collisions, including mass ranges and waveform shapes that line up with known physics. A small subset, however, is harder to classify cleanly. Some events involve component masses that sit in the ambiguous range between typical neutron stars and light black holes. Others show waveforms that are slightly awkward to match with the simplest models. None of this is proof of dark compact objects. The conservative explanation is that we are seeing unusual but still ordinary remnants, but the existence of these outliers keeps the door open to the possibility that at least some mergers involve compact bodies that are not made of normal matter. There is also a potential for indirect signals in certain particle models. If dark matter can annihilate or decay, then a very dense dark object could heat internally or generate faint secondary emissions. Those signatures would be weak and highly model dependent. So far, no observation provides an unambiguous detection of this kind. The conservative expectation is still that most dark compact bodies, if they exist, remain electromagnetically silent. This takes us back to the same kind of blind spot we saw with rogue black holes. The galaxy may contain a large population of massive objects we cannot see directly. They leave little trace unless they happen to lens a background star, disturb a visible system, or merge in a way that produces gravitational waves. We therefore might be living in a gravitational environment shaped not only by smooth halos and visible stars, but also by invisible compact masses moving through the disk and halo. If that population is real, it matters for galaxy evolution. A halo filled with compact dark objects is not a perfectly smooth potential. It becomes a field of discrete masses that can scatter stars, perturb planetary systems, and subtly reshape star-forming regions over long timescales. These effects would be slow and statistical, which makes them hard to isolate observationally, but they are a predictable consequence if dark matter clumps at all. At the moment, dark stars and dark neutron stars are still hypothetical. The argument for them is not that we have seen one. It is that in a self-interacting dark sector, they follow naturally, and their invisibility makes them difficult to exclude. The real test is to tighten gravitational constraints. Deeper, longer microlensing surveys, more precise maps of stellar motions, and a larger catalogue of gravitational wave events. Those data will tell us how much room nature leaves for dark, compact structures and whether they can be stable enough to survive for billions of years. If dark, compact objects exist, the next question is how much mass they could hold and still remain stable. Ordinary matter gives us clear limits. A white dwarf collapses if it exceeds the Chandrasekhar mass. A neutron star collapses if it exceeds the Tolman-Oppenheimer-Volkoff limit. These thresholds come from well-known particle interactions and pressure sources. Dark matter does not follow those rules. Its stability depends entirely on whatever forces operate inside the dark sector, forces we have not measured. If dark matter is truly collisionless, then compact objects cannot form at all. Gravity would pull particles inward, but with no pressure to counteract collapse, the material would either stay diffuse or fall straight into a black hole. But if dark matter includes any form of repulsive interaction or pressure at high density, then a range of stable masses becomes possible. The exact values depend on particle mass, coupling strengths, and the structure of the dark interaction. Even modest changes in those parameters can shift the maximum mass by orders of magnitude. This makes the landscape wide. It also makes it difficult to rule out entire categories of dark objects without clear observational contradictions. One constraint comes from gravitational lensing surveys. Large compact objects, especially those above about a solar mass, are rare, or they produce lensing events that have not been observed at the expected frequency. That rules out a galaxy dominated by dark stars the size of suns, but it does not eliminate smaller populations or objects with masses below current detection thresholds. Another constraint comes from structure formation. If too much dark matter is packed into compact bodies, the cosmic web would evolve differently. Simulations show that a significant fraction of dark matter in stellar mass clumps would alter the distribution of galaxies and the growth of halos. That has not been observed, so the fraction of dark matter locked into large bodies must be limited. Small bodies, however, planetary mass compact objects or clusters of them, remain much harder to constrain. The most ambiguous mass range lies between planets and light stars, roughly 3 to 10 solar masses. Objects in this regime would lens light in ways detectable by long baseline microlensing surveys, but only if surveys run for decades with continuous coverage. Current data give partial coverage. We have strong limits on some masses, weak limits on others, and a wide middle ground where dark compact bodies could exist without violating any known observation. This region of uncertainty overlaps with the mass range of some gravitational wave events whose classification remains unclear, especially mergers involving components around 2 solar masses. If dark objects do populate that mass band, the effect on a galaxy would be cumulative rather than dramatic. A star passing near one would experience a subtle gravitational nudge. Repeated encounters over billions of years could thicken galactic disks, heat stellar populations, and change the orbits of clusters. The effect would be statistical, not catastrophic, slow rearrangements rather than sudden disruption. But for planetary systems, even a single close passage could be significant. A dark object does not need light to destabilize an orbit. It only needs mass and proximity. These ideas connect to an older puzzle. For decades, astronomers have searched for machos, massive compact halo objects, as a candidate for dark matter. Early microlensing surveys ruled out machos as the dominant component of dark matter, but they did not eliminate a smaller population. Dark compact objects, if they exist, would be a modern extension of that idea, just with different internal physics. They would not explain dark matter as a whole, but they could account for a small percentage of the mass budget while remaining almost invisible. That is the key point. Invisibility is not a rare property in the universe. Rogue black holes are invisible unless they lend something or consume matter. Ultra-diffuse galaxies are nearly invisible because their stars are too spread out. Even within ordinary astrophysics, many processes operate below detection thresholds simply because they produce little or no electromagnetic emission. When you build a picture of the cosmos based on light alone, you automatically miss anything that does not shine. This realization pushes astronomy toward new strategies. Light will always be a primary tool, but gravity is becoming equally important. Microlensing, astrometry, and gravitational waves are three methods that do not depend on luminosity. They can detect mass wherever it is, regardless of whether it glows. Over time, these tools will fill gaps in the map of our galaxy. They will reveal whether the Milky Way contains dark structures we have not yet catalogued, and how common they might be. Even if the number of such objects is small, their existence would change how we interpret a wide range of phenomena, from stellar dynamics to galactic evolution. And it would underline a broader theme. The universe is shaped not only by what is visible, but by what is hidden. To understand the next set of threats and mysteries, we need to consider structures that do shine, but suddenly stop shining. Some stars do not explode, they simply vanish, and that phenomenon is even harder to explain. Most stars end their lives in predictable ways. A massive star collapses and explodes as a supernova. A sun-like star expands into a red giant and then sheds its outer layers, leaving behind a white dwarf. Even unusual cases, like neutron star mergers or pair instability supernovae, leave clear energetic signatures. In astrophysics, disappearance without light is not supposed to happen. Yet in the last decade, astronomers have found candidates for exactly that. Stars that seemed normal, showed no signs of instability, and then stopped emitting light with no supernova, no fading remnant, no detectable explanation. The most notable effort to track such events is the project known as Vanishing and Appearing Sources during a century of observations. It compares photographic sky plates from the early 20th century with modern digital surveys. The method is simple. Find objects that existed in older images but are missing today. Most differences come from calibration issues, variable stars, or imaging artifacts. But even after screening those out, a handful of cases remain. Stars that were clearly present in historical data but now seem gone. One of the strongest candidates is a massive star in the galaxy NGC 6946. It was monitored for years, showed a pattern of normal variability, and then faded abruptly. No supernova was recorded. No shock breakout was observed. Infrared imaging revealed only a faint residual glow consistent with dust, but not with a core collapse explosion. One explanation is that the star collapsed directly into a black hole. In that scenario, the core gives way, but the outer layers fail to produce a visible blast. The star simply turns into a black hole with little or no electromagnetic signature. This idea, a failed supernova, has been discussed in theory for years. In some mass ranges, a massive star's core collapse may not trigger the shock needed to blow off its outer layers. Instead, the star implodes. If that happens, most of its mass falls inward, and the result is a quiet formation of a black hole. The process might produce only a dim, short-lived burst of neutrinos or a weak infrared brightening as the remaining envelope settles. From the outside, the star would appear to stop shining between one observation and the next. We do not yet know how common these events are. If failed supernovae occur frequently, they would reshape our understanding of how black holes form. The standard picture holds that massive stars explode first and collapse afterward. But if many collapse directly, the number of black holes would be higher and the mass distribution would shift. This connects directly back to the earlier problem, the population of compact objects in the galaxy. A quiet collapse is an efficient way to create a black hole that leaves no bright remnant. It is also a way to produce black holes in environments where supernova disruption would normally prevent heavy remnants from surviving. Failed supernovae are not the only explanation for disappearing stars. Another possibility involves extreme dust formation. In rare cases, a massive star can eject material that rapidly condenses into thick dust, hiding the star behind an opaque shell. From Earth, the star would look like it vanished, even though it still exists. But such dust-enshrouded phases usually leave distinct infrared signatures, and not all candidate disappearances show those signatures strongly enough. So dust is a partial explanation, not a universal one. There is a more speculative interpretation as well. Some models suggest that interactions with a close companion or a dense cluster environment could destabilize a massive star and remove much of its envelope without producing a typical explosion. In this case, the star may survive as a faint remnant that is difficult to detect with current instruments. These scenarios are harder to verify because they depend on rare initial conditions, but they remain on the table. The most important point is that the disappearance of stars is not an isolated curiosity. It ties into a larger question about how matter cycles through the universe. Every time a star collapses directly into a black hole, it adds to the galaxy's inventory of compact objects. Every time a star dissolves or fades in a way we cannot fully track, it adds uncertainty to our understanding of how stellar populations evolve. And every unresolved case reminds us that luminous matter is only the visible fraction of a much more complex system. If failed supernovae are common, then the Milky Way is producing black holes quietly all the time. These black holes would not be surrounded by expanding nebulae or energetic remnants. They would be born dark, remain dark, and drift through space without announcing themselves, contributing to the silent population of massive bodies that we already know we cannot fully count. The next step is to look at the most striking example of stellar instability, the sudden collapse of massive blue supergiants and the limits of how much mass a star can lose before it disappears. These cases show just how narrow the line can be between an ordinary death of a star and a star that leaves no visible trace at all. Massive stars live fast and die violently, but even among them blue supergiants stand out. They burn through their fuel at extreme rates, maintain high internal pressures, and hover near the thresholds of stability. Small changes in temperature, rotation, or mass loss can push them across boundaries that separate a normal evolutionary track from catastrophic failure. When these stars collapse, they can produce some of the most energetic supernovae known, but they can also fail, ending not in an explosion, but in a quiet implosion that leaves almost nothing visible behind. One of the best studied examples is the blue supergiant Sanjalik 69°202, the progenitor of SN 1987A. It looked unusually compact for a star that was expected to explode. For years, astrophysicists debated whether its properties hinted at a prior merging event or an unstable phase of mass loss. When it finally collapsed, the explosion showed patterns that did not match classic models. Asymmetries in the ejector, a slower than expected shock breakout, and signatures suggesting internal mixing before collapse. SN 1987A was visible and bright, but it revealed how unpredictable the late stages of a blue supergiant can be. Now consider stars of similar mass that undergo the same internal changes, but never achieve the conditions needed for a luminous explosion. Theoretical simulations show a narrow mass range in which a core collapse may fail to generate enough outward pressure to expel the outer layers. If the shock stalls and no revival mechanism succeeds, the star implodes. Most of the mass falls inward and forms a black hole directly. A small amount of material may be ejected, but not enough to produce a bright transient. The visible signature is faint or absent. Such events could explain several candidates for disappearing massive stars. Blue supergiants are particularly vulnerable because they hold large envelopes that can absorb shock energy. If the energy is insufficient to expel them, the envelope chokes the explosion. Instead of an expanding nebula, the outer layers fall back toward the core. For an observer, the transition from a bright star to nothing would happen quickly, potentially over a single observing season. In these cases, the only detectable signal would be a brief neutrino burst, similar to the one recorded from SN 1987A, but far weaker. Neutrinos escape even when photons cannot, but our ability to detect such faint bursts from distant galaxies is extremely limited. Unless a collapse occurs in our immediate cosmic neighborhood, the event passes unnoticed. The result is a black hole born quietly, without the visual drama we associate with stellar death. Blue supergiants also undergo episodes of extreme instability long before collapse. They can shed mass in violent, irregular outflows that create complex shells around the star. These eruptions resemble scaled-down versions of the events seen in luminous blue variables. If a star loses too much mass too quickly, the remaining core envelope structure may become unstable and begin collapsing earlier than expected. Such collapses are not necessarily explosive. They can produce failed supernovae or partial disruptions that leave the star drastically dimmer, heavily obscured, or structurally altered. Distinguishing these pathways requires multi-wavelength follow-up that is often unavailable. The broader implication is that the evolution of massive stars is more diverse than the standard diagrams suggest. We tend to categorize stellar deaths into neat types: Type 2, Type Ib, Type IC, each with expected observational signatures. But real stars do not always behave ideally. Internal rotation, magnetic fields, binary interactions, and mass loss histories introduce complexities that can push a star into unexpected regimes. Some of those regimes may produce nearly invisible outcomes. If quiet collapses are common among blue supergiants, they could contribute significantly to the population of stellar mass black holes in galaxies. Many of those black holes would be born without supernova remnants, without metal-rich ejecta, and without bright transients. They would appear only when they lens distant stars, distort nearby orbits, or merge with other compact objects. In gravitational wave catalogues, they would be indistinguishable from black holes formed through more conventional supernova pathways. This possibility strengthens an emerging theme. The universe may be producing far more black holes than previously assumed, and many of them may be born quietly. Combined with rogue black holes drifting through the galaxy and potential dark compact objects, the picture becomes increasingly complex. The cosmos may be filled with massive bodies that do not shine, each contributing to the gravitational landscape in ways we have only begun to probe. The next step is to look at how these silent populations interact with visible matter, especially in regions of active star formation, where even small gravitational influences can redirect the evolution of entire clusters. Regions of active star formation are some of the most sensitive environments in the galaxy. They rely on a careful balance between gravity, turbulence, and radiation. Giant molecular clouds collapse in fragments, forming dense cores that eventually ignite as new stars. Even small perturbations from outside, a passing shockwave, a nearby supernova, or a shift in local gravitational potential can change the number, type, and distribution of stars that form. When the perturbation comes from a compact object with significant mass, the consequences can be long-lasting. A rogue black hole passing near a star-forming cloud does not need to enter it to have an effect. Its gravity compresses gas on one side of the cloud while stretching it on the other. Simulations show that such tidal forces can either trigger early collapse in some regions or suppress collapse in others. The result is an uneven pattern of star formation, with dense clusters in one area and unexpectedly diffuse patches nearby. If the black hole passes closer, it can pull gas out of the cloud entirely. That gas, once removed, cannot participate in star formation and will drift away or mix with more diffuse interstellar material. The same logic applies to dark compact objects, if they exist. Because they do not interact with radiation, they can move through star-forming regions without slowing down or heating the surrounding gas. Their gravitational influence would be clean and silent, creating distortions that are hard to distinguish from ordinary turbulence. Over the lifetime of a molecular cloud, repeated encounters with even a small population of such objects could shift the initial conditions of star formation enough to alter the future stellar population of that region. Star clusters themselves are also vulnerable. Young clusters contain hundreds to thousands of stars in a relatively small volume. Their internal motions are delicate. Introducing a massive object, even one passing several parsecs away, can inject energy into the system. Some stars may be pushed into wider orbits, some may be ejected entirely, and others may migrate inward. Over millions of years, these small changes accumulate. The cluster becomes more diffuse, its core less compact, and its gravitational structure weaker. If the perturbations continue, the cluster eventually dissolves into the background of the galaxy. This dissolution process happens naturally as clusters age and interact with the galactic tide. But the presence of unseen wandering masses accelerates it. The Milky Way's disk is not empty. It contains black holes, neutron stars, stellar remnants, and possibly dark structures that do not shine. Each one is a gravitational source. Each one can nudge a star-forming region or a cluster off its expected evolutionary track. There is another angle to this problem: feedback from massive stars. In the thriving star-forming regions, massive young stars emit strong radiation and drive stellar winds that carve cavities in the surrounding gas. If a compact object moves through such an environment, it can change how those cavities grow. A small shift in density or pressure can redirect the flow of ionized gas, altering the expansion speed of H2 regions or the shape of the surrounding shells. These changes then cascade into later stages of star formation, influencing where second-generation stars appear and how massive they become. Observationally, these processes are difficult to disentangle. Star-forming regions already display complex geometries caused by turbulence, magnetic fields, and variations in composition. Adding silent gravitational intrusions makes the picture even harder to reconstruct. The only clear signatures would be patterns that deviate from standard simulations: asymmetric collapse, localized voids, unusual mass distributions, or unexpected stellar velocities in young clusters. Such anomalies exist, but they are often attributed to stochastic processes rather than external intruders. Without a direct detection of the perturbing mass, the event remains invisible by definition. The implication is that the evolution of star-forming regions may include contributions from sources we do not track. Over cosmic time, even rare encounters add up. If a giant molecular cloud forms near a population of quiet black holes, whether born from failed supernovae or drifting from elsewhere, its evolution may diverge from similar clouds in quieter areas. The long-term outcome may be a difference in the kinds of stars formed, the frequency of massive stars, or the eventual number of remnants. All of this connects back to the central theme. The universe is shaped by forces and objects that do not announce themselves. The next piece of the puzzle lies in the structures that live between star-forming regions, the vast filamentary networks that trace the cosmic web. These immense structures can amplify or suppress the influence of hidden masses on scales far beyond individual star systems. On the largest scales, the universe forms a pattern known as the cosmic web. It is a network of filaments, sheets, and voids created by the distribution of dark matter. Galaxies sit inside these filaments like beads on extended gravitational strands. Gas flows along the filaments, feeding galaxies and fueling new star formation. Between them lie vast voids, low-density regions where gravity is weak and matter is sparse. This structure is stable over billions of years, but it is not static. As matter pulls inward along filaments, the web slowly evolves, amplifying small differences and transmitting gravitational influences across enormous distances. Because the cosmic web is shaped by dark matter, anything that alters the behavior of dark matter alters the shape of the web. If even a small fraction of dark matter clumps into compact objects, then filaments become slightly more irregular. Instead of smooth gravitational channels, they become rough, with small but numerous perturbations scattered along their length. These irregularities can redirect gas flows, change collapse rates, and shift the timing of when galaxies receive new material. Over hundreds of millions of years, those shifts influence how galaxies grow, when their star formation peaks, and how quickly they build heavy elements. In simulations, most of these effects are subtle. The motion of gas along filaments depends on many factors: temperature, shock waves from early star formation, the activity of central black holes, and the overall gravitational landscape. But when compact masses are introduced into the models, the behavior changes in predictable ways. Gas becomes more clumpy. Flows break into smaller streams. Shock fronts propagate asymmetrically. The system becomes more chaotic on small scales and more uneven on large scales. These patterns closely resemble some observed structures that standard models, using only smooth dark matter, struggle to reproduce. One example is the presence of unusually thin or fragmented filaments seen in some galaxy surveys. These filaments appear more irregular than predicted by purely collisionless dark matter. While there are several possible explanations, feedback from active galactic nuclei, early heating from ultraviolet radiation, or past mergers, the idea that compact masses contribute small gravitational disturbances along the filaments is consistent with the observed deviations. A compact object moving through a filament can distort local density enough to change how nearby gas collapses, even if the object itself remains invisible. Voids also respond to hidden structures. Voids are not completely empty. They contain diffuse gas, faint galaxies, and dark matter. Because the matter density is low, even small gravitational influences can have noticeable effects. If compact dark objects drift into a void, they will not create bright signatures, but they will pull on nearby material. Over billions of years, those gentle tugs can shift the shape of the void, changing its boundaries and introducing gradients that do not appear in simulations of purely smooth matter. Observationally, some voids show density patterns that remain difficult to match without adding additional, small-scale gravitational sources. These considerations matter because the cosmic web controls the flow of material that feeds galaxies. If the web evolves differently in the presence of compact bodies, whether black holes, failed supernova remnants, or dark objects, then galaxy evolution also changes. A galaxy receiving gas slightly earlier or slightly later than expected can end up with a different star formation history. Over time, these differences accumulate into large-scale variations, changes in the number of massive stars, the growth of central black holes, and the chemical composition of entire galactic populations. There is another consequence. Filaments act as highways not only for gas, but also for gravitational disturbances. A compact object moving along a filament can influence material far from its immediate path. The perturbations propagate outward, altering collapse rates in distant regions. Because filaments span tens to hundreds of millions of light years, a single object can affect structures separated by enormous distances, not strongly, but steadily. This long-range influence is one of the reasons the cosmic web is such a powerful amplifier of small effects. Modern surveys like DESI and Euclid are mapping the cosmic web in unprecedented detail. They reveal fine structures in filaments that were previously invisible, including small density dips, asymmetric threads, and branching patterns that do not always match the classic predictions of smooth dark matter. These anomalies are not proof of compact dark bodies, but they show that the large-scale structure may be responding to influences we have not fully modelled. If silent massive objects contribute even slightly to the evolution of the cosmic web, then their impact extends far beyond local star-forming regions or individual galaxies. They become part of the architecture of the universe itself, shaping its long-term evolution without ever emitting a photon. Understanding this influence is essential, because the web controls much of what happens inside it, from the birth of galaxies to the environments where stars and planets form. The next step is to examine a smaller scale where invisible influences become even more pronounced: the centers of galaxies. Here, supermassive black holes dominate, and even slight variations in their feeding patterns can transform entire galactic populations. At the centers of galaxies, gravity reaches its highest concentration outside of the early universe. Almost every large galaxy hosts a supermassive black hole with a mass millions or billions of times greater than the Sun. These black holes regulate the evolution of their galaxies by controlling how gas flows, how stars are distributed, and how often new stars form. Their influence extends far beyond their immediate surroundings, because even slight changes in how they accrete matter can alter the structure of the entire host galaxy. Most of the time, a supermassive black hole grows slowly. Gas drifts inward, heats up, and emits radiation as it spirals into the event horizon. If the accretion rate is stable, the galaxy remains relatively calm. But if something disturbs the environment, an inflowing gas cloud, a disrupted star, a merger with another black hole, or a passing massive object, the system can switch into a different accretion regime. The radiation output rises sharply. Jets strengthen. Gas flows reorganize. What follows can affect the galaxy on scales thousands of times larger than the region around the black hole itself. Active galactic nuclei, AGN, are the most visible expression of this process. When a supermassive black hole begins consuming material at a high rate, it produces enormous outflows that heat and scatter gas throughout the galaxy. These outflows can shut down star formation by preventing gas from cooling, or they can compress gas in certain regions and trigger new star formation bursts. The balance between these effects determines whether a galaxy becomes a quiet gas-poor system or a turbulent star-forming one. But AGN are only one part of the story. There are also the quieter phases, the transitions that do not produce bright jets or enormous radiation outputs, but still change the physical conditions of the galactic core. A small adjustment in the feeding pattern of the black hole can realign gas streams, shift orbital resonances, or alter the density profile of the inner region. These effects propagate outward, especially in galaxies where the central gravitational potential dominates the motion of stars within several hundred parsecs. Hidden massive bodies, wandering black holes, dark compact objects, or remnants of failed supernovae can contribute to these disturbances. If one of them passes through the central region, even at some distance, its gravitational pull can redistribute angular momentum among gas clouds. That redistribution may divert material toward the supermassive black hole or away from it. In either case, the accretion rate changes. If that change persists, the galaxy's star formation history changes with it. This interaction is not limited to wandering masses. A galaxy can also experience disruption when it absorbs smaller satellite galaxies. These satellites often contain their own black holes. When a satellite sinks toward the center due to dynamical friction, its central black hole can merge with the primary one. Mergers release gravitational waves and send recoil velocities through the resulting remnant. In some cases, the recoil is strong enough to displace the supermassive black hole from the galactic center. Such offsets have been observed in a few galaxies as spatial shifts in the position of the AGN relative to the stellar core. If a supermassive black hole is displaced, even slightly, the entire inner region of the galaxy rebalances around its new gravitational center. Gas flows change direction. Star orbits adjust. Over millions of years, the displacement reshapes the structure of the galactic core. If the black hole oscillates around the center or slowly returns to equilibrium, the process repeats, imprinting a complex dynamical history on the surrounding stellar population. Compact objects drifting in the central region can also interact with the stellar distribution directly. A sufficiently massive object can scatter stars, leading to changes in the density profile of the galactic nucleus. Some nuclei show depleted cores, regions where fewer stars remain than models predict. One explanation is repeated interactions with massive intruders that removed stars from the central region through gravitational encounters. These silent interactions accumulate over cosmic time. Even a small number of undetected massive objects can change the central structure of a galaxy enough to influence its long-term trajectory. The relationship between the supermassive black hole and its host is therefore not fixed. It evolves with every mass that enters the central region, every merger, every shift in the inflow of gas. Understanding these dynamics is essential because the centers of galaxies act as regulators for the rest of the system. If the core becomes unstable, the entire galaxy feels the consequences. The next step is to examine how these processes influence large populations of galaxies, and what happens when the behavior of supermassive black holes changes across the universe as a whole. When we step back from individual galaxies and look at the universe on population scales, a clear pattern appears. Galaxies do not evolve in isolation. Their growth, their star formation rates, and the activity of their central black holes all shift over cosmic time in ways that trace broad, coordinated trends. Some of these trends are driven by environment, mergers, inflows along filaments, and interactions within clusters. Others arise from internal feedback cycles. But a growing body of evidence suggests that subtle silent processes may also contribute. These are processes that do not produce bright signatures, but still influence how galaxies age across billions of years. One such trend is the decline of star formation in massive galaxies. In the early universe, gas was abundant and flowed freely into young systems. Star formation rates were high. Over time, that flow slowed. Today, many massive galaxies are quenched, meaning they form few or no new stars. AGN feedback explains part of this. Intense outflows from an active supermassive black hole can heat or expel the gas a galaxy needs to form stars. But not all quenched galaxies show signs of strong AGN activity. Some appear quiet, with no obvious source of the energy needed to stop cooling. Small gravitational disturbances may fill some of that gap. If a galaxy contains wandering black holes, dark compact objects, or remnants of failed supernovae, each one can subtly heat the stellar population through repeated gravitational encounters. This process, called dynamical heating, increases stellar velocities and thickens galactic disks. Over long periods, dynamical heating can prevent gas from settling into stable configurations required for sustained star formation. It is a cumulative effect, faint, silent, and difficult to isolate, but consistent with the long-term changes seen in some galactic populations. There is also the issue of galactic cores. Some galaxies have central regions that are unusually large and diffuse. Others have sharply peaked cores with extremely dense stellar concentrations. The diversity of core structures has been linked to different growth histories, but not all cases are easy to explain with mergers alone. Hidden compact objects could contribute by reshaping stellar distributions over time. Even a single intermediate mass black hole recycling through the central region can displace thousands of stars through gravitational interactions, leaving a lasting imprint on the density profile. Cluster environments add another layer of complexity. Galaxy clusters are the most massive gravitationally bound structures in the universe. They contain hundreds to thousands of galaxies, embedded in enormous quantities of dark matter and hot gas. Within clusters, galaxies experience strong tidal forces, high collision rates, and accelerated evolution. But the intracluster medium also contains a population of unseen masses, wandering black holes, old neutron stars, and possibly dark compact objects lost from disrupted galaxies. These bodies move through the cluster for billions of years, interacting with member galaxies in ways that are small but cumulative. Their presence can alter the orbits of galaxies, add noise to the cluster's mass distribution, and contribute to the stripping of gas from vulnerable systems. On cosmic scales, small perturbations add up. If a few % of the universe's mass exists in compact bodies that do not shine, their collective gravitational influence could contribute to the observed diversity in galaxy shapes, the irregularities in the cosmic web, and the long-term decline in star formation activity across many environments. None of these effects would be dramatic in isolation. Together, they could help explain astrophysical trends that currently lack clean, single-cause explanations. All of this points toward a broader conclusion. The visible universe, the stars, nebulae, and galaxies we observe directly, is only a partial map of what is actually shaping cosmic evolution. The invisible population of massive objects, from rogue black holes to dark sector structures, may play a role in everything from the collapse of molecular clouds to the growth of central black holes and the aging of galaxy populations. To understand the final pieces of this picture, we need to consider the rarest events in the universe: collisions between compact objects. These mergers do more than produce gravitational waves. They reshape their surroundings, seed new black holes, and can even modify the long-term energy balance of entire regions. Collisions between compact objects are among the most energetic processes in the universe, yet most of their influence is gravitational rather than luminous. When two black holes merge, the event can release more energy and gravitational waves than all the stars in the observable universe emit in light during the same moment. These waves ripple outward, carrying information about the masses, spins, and orbital histories of the merging bodies. But the merger itself leaves almost no electromagnetic signal. The result is a massive remnant, a heavier black hole, and a gravitational imprint that propagates across cosmic distances. The discovery of gravitational waves in 2015 opened a new window into these events. Since then, LIGO, Virgo, and Kagra have catalogued scores of mergers. Most of them involve black holes, though neutron star mergers and mixed mergers have also been observed. A consistent pattern has emerged. The universe produces far more black hole mergers than expected from traditional binary evolution models alone. Something is feeding the population of merging black holes. Either black holes are forming more frequently than previously assumed, or they are being brought together more efficiently. One mechanism is dynamical assembly. In dense environments such as globular clusters, or the cores of young massive clusters, black holes sink toward the center through mass segregation. Once there, repeated gravitational interactions can create temporary binaries that harden over time. Eventually, some of these binaries merge. This process can explain mergers that occur in environments populated by many heavy remnants, but it does not explain all events observed so far. Another mechanism involves the wandering population, rogue black holes, failed supernova remnants, and possibly dark compact objects. If such bodies move through dense stellar regions, they can perturb existing binaries or capture companions gravitationally. Encounters between multiple massive objects can lead to chaotic three-body interactions, during which one object is ejected and the remaining pair becomes more tightly bound. Over millions of years, these interactions can funnel black holes into merging configurations that would not arise from isolated binary evolution. The mergers themselves have consequences that extend far beyond the event horizon. Every merger releases a recoil kick, a velocity imparted to the remnant due to asymmetries in the gravitational wave emission. Depending on the spins and masses of the merging black holes, the recoil can reach hundreds or even thousands of kilometers per second. In small galaxies or star clusters, a recoil this strong can eject the remnant entirely. Ejected black holes become wanderers, adding to the population of massive bodies drifting between stars or even between galaxies. In larger galaxies, a recoil may not eject the black hole, but can displace it from the center. The remnant oscillates through the galactic core for tens or hundreds of millions of years until dynamical friction brings it back into equilibrium. During this time, it disturbs the surrounding stars, redistributes angular momentum, and sometimes temporarily disrupts accretion. These effects can alter the appearance of the central region and contribute to the diversity observed in galactic nuclei. Neutron star mergers introduce another important element: heavy element production. These mergers are a primary source of R-process elements such as gold, platinum, and uranium. The distribution of these elements gives clues to where and when mergers occur. Some galaxies show enrichment patterns that do not align neatly with star formation histories, suggesting that compact object mergers may happen in unexpected environments. potentially influenced by populations of compact objects that drift into new regions before merging. There is also the question of mixed mergers, black hole neutron star collisions. These events are rare but informative. Depending on the mass ratio, the neutron star may be tidally disrupted before crossing the black hole's event horizon. When this happens, it can eject material that produces a faint electromagnetic signal and enriches the surrounding environment. But if the neutron star is swallowed whole, the merger produces no light at all. These dark mergers add to the population of heavier black holes while leaving no visible trace. As gravitational wave detectors become more sensitive, they will reveal smaller mergers, more distant events, and potentially populations of compact objects we have not yet detected. If dark compact objects exist, their mergers would produce gravitational waves as well. Waves that would look like black hole mergers, but with slightly different signatures. Distinguishing these cases will require extremely precise measurements of waveforms, but the possibility reinforces a consistent message. The universe contains more compact objects than we once assumed. Mergers are the engines that recycle compact objects into heavier remnants. Over cosmic time, these remnants accumulate into a population of massive black holes that quietly shape galaxies, star clusters, and the cosmic web. The final piece of the picture is the long-term future of these compact populations, how they drift, collide, grow, and influence the evolution of the universe across its deepest timescales. Over the longest timescales, compact objects become the dominant form of matter in the universe. Stars burn out. White dwarfs cool. Neutron stars decay through slow processes such as proton emission or hypothetical quantum transitions. What remains are black holes and any other compact bodies that may exist, including dark sector objects if they form. These remnants are stable on timescales far longer than the current age of the universe. As everything else fades, they take over the cosmic landscape. In the near future of cosmic evolution, meaning the next trillions of years, black holes will continue to merge. Galaxies that still contain gas will slowly feed their central black holes until the supply is exhausted. Smaller black holes will drift inward through dynamical friction and eventually be consumed. Intermediate mergers between wandering black holes will occur across the galaxy, especially in dense remnants of star clusters. Each merger increases the mass of the remaining black hole and reduces the overall number of objects. The distribution becomes more top-heavy, fewer bodies, each more massive. If dark compact objects exist, they follow the same path. They drift through the galaxy, occasionally collide or capture companions, and either merge or remain bound in long-lived binaries. Over extremely long periods, their interactions also prune the population. Like black holes, they accumulate mass through mergers, creating a parallel population of heavy remnants, invisible but gravitationally influential. In galaxy clusters, the process becomes more dramatic. Clusters gradually lose energy through gravitational interactions. Member galaxies spiral inward and merge. Their central black holes eventually coalesce into single enormous black holes, weighing billions of solar masses or more. These giants dominate the gravitational landscape of the cluster. Smaller compact objects orbit them for eons. occasionally merging or being ejected into intergalactic space. Each ejection adds to the population of wanderers traveling through the cosmic web. As time goes on, mergers become rarer, but not zero. The largest black holes spend long periods isolated, but any compact object that drifts too close will eventually be captured. The gravitational environment becomes simpler. Fewer bodies, cleaner trajectories, more isolation. The universe enters an era where most of the remaining mass is locked in a relatively small number of extraordinarily massive objects, separated by vast distances. On even longer timescales, the picture narrows further. If Hawking radiation is real, all black holes slowly lose mass through quantum processes, radiating energy at a rate inversely proportional to their mass. For stellar mass black holes, this evaporation takes much longer than the current age of the universe. For supermassive black holes, the timescale is vastly larger, up to 10 to 100 years or more. As they evaporate, they shrink. Eventually, in the final stages, they radiate away their remaining mass in a brief burst of high-energy particles. If dark sector compact objects exist, their fate depends entirely on their particle physics. They may be stable indefinitely. They may decay through channels unknown to ordinary matter. They may evaporate analogously to black holes if their internal structure allows it. Without direct detection, these questions remain open, but the general trend is the same. Over long enough time, compact remnants are the final actors. Across these timescales, the role of silent massive objects becomes increasingly important. They shape the motion of galaxies in the present, the structure of clusters in the far future, and the long-term evolution of the universe itself. As everything else cools, dims, and fades, compact objects remain as the final form of structure. The gravitational anchors of a universe running out of energy gradients. Eventually, the universe enters what cosmologists call the degenerate era. Ordinary processes stop. No new stars form. Gas is exhausted or ionized beyond recollection. Only compact remnants, black holes, neutron stars, dark objects, and the most stable forms of matter continue to interact gravitationally. When these bodies finally decay, whether through quantum effects or unknown dark sector processes, the universe transitions into its final stage, a near-empty expanse where only the faintest traces of structure remain. This long-term outlook connects every theme we have explored: silent objects, invisible processes, and the gravitational pathways that operate without light. In the end, what shapes the universe is not what shines, but what endures.